Hey everyone, welcome to this explainer. I'm your tutor, and today we're going to crack the code on the language of machines. We are getting you fully prepared for your IGCSE computer science exam by breaking down exactly how data is represented under the hood of your computer. We'll be moving from the everyday human numbers you already know, straight into the binary and hexadecimal systems that power absolutely all of modern technology. Let's get to work.
Okay, so here is our game plan for today. We'll meet the number systems, tackle denary and binary conversions, check out the hexadecimal shorthand, do some hex conversions, and finish up with an IGCSE practice quiz.
All right, Section 1, let's meet the number systems.
So before we dive into the math, here's some really good news straight from your syllabus. We're only dealing with positive integers today, and we max out at a 16-bit binary length. Phew, that makes these conversions way simpler. For the exam, you're responsible for understanding three specific systems: denary, which is base 10, binary, which is base 2, and hexadecimal, which is base 16.
It really boils down to this fundamental difference. We humans use the denary base 10 system, right? We count using 10 digits, 0 through 9. But a computer? It's basically a giant box of billions of tiny microscopic switches that can only ever be either off or on. So they have to use a base 2 system consisting entirely of zeros and ones, which we call bits.
Moving into Section 2, denary and binary conversions.
So think of an 8-bit binary system like this. Your column headings start at 1 on the far right, and they literally just double every single time you move to the left. It goes 2, 4, 8, 16, 32, 64, all the way up to 128. To turn binary into denary, you simply add up the heading values wherever a 1 appears. For example, if we have 1 sitting under 64, 32, 16, 8, and 1, we just add those together and boom, we get a denary total of 121. It's honestly just basic addition.
Now, to flip it and go from a human denary number back to computer binary, the syllabus gives you two approved methods. You could do the divide by 2 trick, where you just keep dividing your number and jotting down the remainders, or, and honestly this is my personal favorite, just draw out those place value columns from 128 down to 1. Then you subtract the biggest column value that actually fits into your target number, pop a 1 in that column, and just keep chipping away at the remainder until you hit 0.
All right, Section 3, the hexadecimal shorthand.
Okay, just imagine having to read a massive 16-bit binary number like this every single day. Or trying to type it out without making a single typo. It is a total nightmare for programmers. And that is exactly why the hexadecimal base 16 system was created as a shorthand. It's not actually for the computer, it's 100% for us.
So how does it actually achieve this compression? Well, since it's base 16, it needs 16 totally unique symbols. It borrows the familiar digits 0 through 9 for the first 10 values. But then, to represent denary values 10 through 15 with just one single character, it uses the letters A through F. It's such a brilliant trick because it lets us squish any 4-bit binary sequence, which holds a max value of 15, into just one single hexadecimal character.
Which brings us to Section 4, hexadecimal conversions.
Converting a long string of binary to hex is actually super logical. Step 1, you just chop the bits into groups of 4, which, fun fact, programmers playfully call nibbles, and you always start doing this from the right side. Step 2, if your very last group on the left is short of 4 bits, just pad it out with zeros. And Step 3, translate each little 4-bit group into its single hexadecimal equivalent.
Let's actually try that on the monster binary number we looked at earlier. We split it up into 4 nibbles. 1011 is 11 in denary, which translates to B in hex. 1111 is 15, which is F. 0000 is just 0, obviously. And 1001 is 9. So that giant, confusing 16-bit string just elegantly turns into 4 hex characters, BF09. Way easier to read and write, right?
Now, what if we need to reverse it and go from hexadecimal directly back to denary? Well, because hex is base 16, our place value headings change. Going from right to left, they are 1, then 16, then 256. You just multiply your hex digits by these new base 16 headings and add the totals all up. But hey, don't forget the golden rule here. Always swap those letters, like A or B, back into their denary numbers, like 10 or 11, before you do the multiplication.
Okay, time for Section 5, the IGCSE practice quiz. Let's test your active recall with some practical questions straight from the syllabus. No calculators allowed in this exam, by the way, so rely on your mental math. Grab a pen, Pause the explainer right here and try calculating the Denary value of the hexadecimal 45A. Remember those column headings we just talked about? 256, 16, and 1. Go ahead, I'll wait.
All right, let's see how you did. Your left digit is 4, so 4 times 256 is 1024. The middle digit is 5, so 5 times 16 is 80. And the right digit is A. Remember, A equals 10, so 10 times 1 is just 10. Add all that up, 1024 plus 80 plus 10, and we get a grand total of 1114 in Denary. Awesome job if you nailed that.
Let's try another one. Convert the Denary number 36 into hexadecimal. And here's a massive hint straight from the syllabus. Use binary as a stepping stone. Pause it and give it a shot. Okay, so the absolute smartest move here is to map that Denary 36 into an 8-bit binary string first. 32 plus 4 gets us 36, so our binary is 00100100. Then we just chop that into two 4-bit nibbles. The left nibble gives us 2, the right gives us 4. Boom, our final hexadecimal answer is 24. Going through binary first makes the whole thing pretty much foolproof.
Final quiz question, and this one tests your actual conceptual understanding. Why do programmers even bother writing in hexadecimal at all if the machine processor only speaks in binary zeros and ones? Pause and think about your answer.
Yep, it's exactly what it sounds like. It's completely for our benefit. It's just a human shorthand. Crushing 4 bits down into one single character makes reading data faster, keeps code looking super clean, and honestly, it prevents so many frustrating typos.
So, you've totally conquered the positive conversions required for your exam, and you officially speak the baseline language of computers. But it does leave us with a pretty wild puzzle. If a machine literally only has ones and zeros, and there's no such thing as a minus sign in the hardware, how on earth does it represent a negative number? Well, that's where a super clever system called 2's complement comes in, and we'll be tackling that exact mystery in our next study session. Until then, keep practicing those conversions, and I'll see you in the next explainer.